how it's going to go right tomorrow.
Yeah, so sorry the coffee break was a disaster. Apparently I cannot be the host of 3 Zoom meetings simultaneously, which I think some people here knew already, but I did not. So tomorrow things will be set up exactly the same way. We're gonna have 3 different people on our end host the 3 different coffee meetings. So everything should work normally tomorrow. The only change to expect is that I'll update the links in the Slack general channel with the new rooms. So sorry about that. Hopefully tomorrow will go smoother.
Okay, so welcome back, everybody. I'll just say a few words about the next lecture. So the next lectures are on the standard model, not on cosmology, if you didn't pay attention to the schedule. And the schedule changed, so we're happy that Ayres agreed to talk in the first week instead of the second week. So Ayres is an expert on electroweak precision calculations, including simulations in E+ E- machines and hadronic machines. And he will be telling us about the standard model and related topics. So
all right, thank you. Yeah, ready when I am. Okay, coffee break is over. I can erase this. Even though the title in the schedule says the standard model of particle physics, I won't give you like a textbook introduction into the standard model because I believe you all have that already from the past. Rather, in this lecture, I want to focus on the area of electroweak precision physics. And to get there, I will go through 3 main chapters. The first one being a bit of a discussion of renormalization. And of course, you probably know the basics of renormalization as well, but there are actually a number of subtleties that are interesting that also help us to learn a bit the structure of the standard model and also to understand of what we may call input parameters in the standard model. I should say off. And after we go through that, the second chapter will be about so-called electroweak precision observables. So I will talk a bit about what they are, how they are measured, what they tell us. And in the end, in the third chapter, I want to connect what's actually the theme of this TASI school, which has to do with dark matter and neutrino physics. So here we want to use what we learned in the first 2 chapters to look at tests of both the standard model and of physics beyond the standard model. And for beyond the standard model, I will in particular focus on ways how one can test models of neutrinos and dark matter, and what electroweak physics can tell us about that. I have posted lecture notes on the wiki page, and I will always continue posting them ahead of the lectures where they are covered. The idea is that you don't have to copy everything that I scribble here on the Zoom screen share. And instead, you can focus on actually what I'm saying or what is being discussed. And talking about what I'm saying, I have enough material to keep blabbering for the entire time that is assigned to me. But I want to ask you to please interrupt me whenever you want to discuss any of the topics that I talk about more, or when you feel, what I'm talking about is too standard and maybe we can skip ahead to something that's more interesting. So this is really for you, it's not for me. Okay, so then let's get started with the first chapter about renormalization. And to set the scene, I will actually start pretty basic, just with renormalization in QED, quantum electrodynamics. This is, of course, the way how renormalization is introduced in a textbook at the first time. I'm just going over it so, that we remind ourselves a little bit, what was happening there, get familiar with the language again. So basically have then be warmed up for what comes afterwards in the full standard model. If you find this is really, going too slow or too boring, just let me know, and I will adjust to that. Before I get started with QED, I should quickly mention a few conventions that can always trip things up. So for the metric tensor, I used the convention that this is a diagonal matrix, which along the diagonal has the entries +1, -1, -1, -1. And that's the same convention that Donald used this morning, so that's good. And for the gamma matrices, we have 4 regular Dirac matrices, which have the anti-commutation rule, 2 times metric tensor times the unit matrix in Dirac space. And they all commute with gamma 5. When one goes to dimensional regularization, of course, the treatment of gamma 5 gets rather interesting, and one can have a lot of discussion around that, which I won't really cover in my lecture, but if you want to know more about that, you can ask me in the discussion session later this week. So the Lagrangian of QED has essentially 2 terms, one involving the gauge field, so this F mu nu, as you all know, is defined as derivative of the gauge field minus the same thing, oops, with the indices flipped. And then we have the corresponding term for the fermions, kinetic term, and mass term. And in order to couple these 2 fields, we also put this interaction term here. So as you can see, this Lagrangian has 2 parameters. The coupling strength, which I call E0, and the mass of the fermion, which I call E0. I put a subscript 0 to all of these quantities, the fields and the parameters in this Lagrangian, because, and that's the basic idea of renormalization, the Lagrangian parameters are not necessarily corresponding to what we observe in an experiment. In fact, they may differ. From the observable parameters, which are called E and M without the subscript 0. And the relationship between those two can be written as follows. We have basically a proportionality constant, Z sub E, between the Lagrangian parameter and the physical coupling, the physical charge. The idea is that this constant is close to 1, so it's 1 plus a small correction delta ZE. And there's a similar relation for the mass. So the mass parameter in the Lagrangian is given by the actual physical mass. And here, instead of multiplying, it's conventional to add an additional piece called delta M. So these two things, this delta ZE and the delta M, they are called counterterms. Now, the question is, well, if we want to make predictions in this theory, we need to know what these counterterms are and how do we determine them. So let me begin with the mass. Oops. No, that happened. So let me begin with the mass. So we have to look at how we actually measure the mass. And its measurement is related to the fact that we find the mass as the pole in a propagator. So if I write the propagator of a fermion as this form, I divided by p/-m, if I multiply both numerator and denominator with p/+m, then I get p² - m² in the denominator, and you can see if now the momentum p² equals m², which is called on shell, then this propagator blows up, which means there's a peak in the probability for observing this particle. So that's basically how we would measure its mass. We just look at electrons with different momenta, and if there may be some distribution because of interactions and smearing and so on and so forth, but it should have a peak at the correct mass. So that's how we would measure it. Now, how we can connect it to actually how we could compute the mass. For that, we need to include higher order corrections. Diagrammatically, we would have the tree-level propagator, which is in Feynman diagrams just a line. And then we have self-energy corrections. At this point, I'm not really saying what particles run in the loop of this self-energy. I just put a generic blob. We could also have multiple self-energies, 2 of them and more. If I express the same thing as a formula, the tree-level propagator is given by I divided by p/-0, the mass in the Lagrangian. Then we have the term with the self-energy. I denote the self-energy by a sigma and another propagator. And so forth. The term with 2 self-energies. And if you stare at this, you might see that this actually forms a geometric series, which we can sum up. And when we do that, this self-energy sigma ends up in the denominator. This also goes under the name of Dyson summation or Dyson series. Now, this symbol sigma is something that exists in Dirac space. So just like the P slash, it involves the Dirac matrices, so it's a 4x4 matrix. The same is true for sigma. And if that's the case, we can basically expand out what are the possible Dirac matrices that can occur inside of it. So the first term I could get is basically one that doesn't contain any gamma matrix. I call it sigma S for scalar. And Lorentz invariance then tells us that this can depend only on the momentum in terms of the momentum squared, P squared. It has to be something that's Lorentz invariance.
Yeah, there's a couple of questions in the chat when you have a second.
I do not see them.
They're in the Q&A section. I can read them off too.
Oh, in the
if you need.
Q&A, I see. I didn't know the Q&A was also used. Okay, I need to bring that up then. So. Okay. So are we basically using all three of those interaction things at the same time? Hello?
I think the answer is yes.
Yes, okay. To see how I can fit them all in my screen. Okay. The mass in the propagator is the bare mass then. So where I wrote the Dyson series, yes, the mass in the propagator is the bare mass. When I talked about at the beginning, the propagator that we actually compared to the measurement, this is actually the renormalized mass and without a zero. And we will see in a second how the two connect. Second question, why are we always guaranteed to get a geometric series? I don't think there's a formal reason that we are guaranteed to get one. It just comes out that way if we compute these things one by one, because it's basically just a chain that we connect bubble by bubble. So I think the formula would be there. A third question, when we do the Dyson series at fixed order, we are taking some higher order graphs, but not all. Is this just a mathematical trick to have the self-energy in the denominator? I guess the question is referring to the fact that we only have self-energy corrections and not vertex corrections. Is that right? What it is about? Julie, shall we unmute Julie? Oops, where did it go?
Hi, I asked a question. So yeah, I was just wondering because in the first graph you could have a two-loop correction.
Aha, okay. Now I understood the question.
This
Okay,
would be the same order as the two bubbles.
Yeah, so this blob, this shaded blob that I drew was not supposed to be specific about any loop order. So it can contain one, two loop, any number of loops.
But when we do it at fixed order, so at one loop, for example.
So I come to actually expanding these things in loop orders a little later. So at this point, I basically keep all orders and perturbations together.
Okay.
And also this decomposition that I'm just talking about into, Dirac form factors, like, I wrote the scalar and so on. That's for all loop orders.
Okay.
And we have one more question. The self-energy here is at one loop level of full order. I guess that's the same, right? So the self-energies includes all loop orders at this point. And one more. In order to see the effects of the self-energy on the analytic structure, we have to take the whole series. Is there anything deep to be said about why we need the whole series? I'm not quite sure where this question is going, but I think, you know, the tricky part by that is actually asking a question, are we allowed to resum them the way we do? How do we know that this geometric series is actually convergent? It would be convergent if the self-energy is small, but as you may all know, why that in principle is the idea of perturbation theory, that the self-energy is small. There are all these issues that, you know, before we do renormalization, it is in principle not small, and it depends on the regularization and so on and so forth. So there's a little bit a leap of faith that we do in saying we assume that this series is convergent and we can sum it up like this. Wow, there are lots of questions about this. I'm amazed. Should the bubble diagram be one particle irreducible? Yes, that's what it is, one particle irreducible. What about the possibility of diagrams with multiply connected blobs? So that's basically kind of the same that we just had. Are these blobs one particle irreducible? So that's what they are supposed to mean. If you have any diagrams where you need to cut more than one line in order to separate them into two pieces, these would all go inside the blobs because they would all make loops. So all the loops are inside the shaded blobs. Okay, very good. Just thinking how I keep all those things on my screen at the same time.
If it's too many things to juggle, we can move the questions only to chat or only Q&A, whatever you prefer.
Chat would be easier, I would say.
Okay, so please from now on only ask questions in the chat. Thank you.
Okay, great. Okay, good. So now, besides a piece that doesn't depend on any Dirac matrix, we can also have one that involves one Dirac matrix that has a Lorentz index mu. So in order to produce something that has the right Lorentz transformation properties, we need to contract that with something else that also has a Lorentz index. The only thing that we really have available is the 4 momentum mu. So there needs to be a p mu. And then there can be a coefficient, which again can depend on p squared. I call it sigma v for vector. That's the vector part of the self-energy. Then there may be also similarly a term with 2 gamma matrices. Each of them we contract with another p. And I call that sigma t, again p squared, the coefficient of that. But that, as a matter of fact, is nothing new anymore, because if we use the basic anti-commutation rules for gamma matrices, you can easily see that this is equal to p squared. So overall, this whole term here is just something that depends on p squared, and therefore this can be absorbed in the scalar part. So we really don't need to carry this along anymore. And the same is true for any terms that have more down to something with 0 or 1 gamma radius. So we only have these two form factors, the scalar and the vector part. Okay, now that we have this, let's go back to our renormalization condition that the physical mass m is supposed to be the pole in the propagator. So we're looking at the pole for p squared equals m squared. Then we get that that's the condition we are supposed to fulfill. Okay, so I see another question, can gamma 5 appear in this construction? That's a good question. So in principle, if this fermion would have different interactions for the left and right-handed part, as is the case in the standard model, then one may need to distinguish those. So instead of 2, one would get then in total 4 form factors. In QED, we don't need to do that because there's no parity violation. We are just okay with 2. Okay, so we want p squared equals m squared. This is when this propagator blows up. As we see from the equation on the top, that is equivalent to actually saying p slash equals m. Then in the form of the expression on the left-hand side, it blows up. And so let's see what happens if we plug that into the denominator of our propagator. So we have p slash minus m0. And now I write m0 as m plus delta m. And then plus the self-energy. And I write the self-energy out in terms of its form factor. So the scalar part and the vector part. And if p squared equals m squared, all of this is supposed to be 0. Now we see the first two terms, p slash minus m, they would be 0 then in that case by themselves. Also the p slash that we have in front of sigma v would become m. So there's some simplifications that occur. And now we can use this expression to derive a condition for our counter term delta m. So we move delta m to one side of the equation and we see this becomes m times sigma v. Now for p squared equals m squared plus sigma s m squared. Good. So this would be how we get a mass counter term. And if we use this mass counter term in our theoretical calculations, then we are basically guaranteed to get a mass in our final prediction that we can relate to experimental observations. Another question. Did you redefine sigma v or does p slash become m? So in this last step, well, if I'm looking for the pole where p squared equals m squared, and then I look at this equation up here, so if p squared equals m squared, you can clearly see on the right-hand side that it blows up, right? There you can see the pole in the propagator. If I look at the form on the left-hand side, this tells me when p squared equals m squared, it must also mean that p slash becomes equals to m. Otherwise, the left-hand side would not have a pole. But of course, since if this is equality, both sides need to have a pole. So it's not a redefinition of sigma v, it's just I'm picking a particular value of the momentum where the particle goes on shell. Good. So this was the mass. Now we have another parameter to renormalize, which is the coupling or the charge, E. So we also need to have some condition that we can relate to experiment. And the conventional condition for that is to look at the strength of the coupling in the so-called Thomson limit. What is the Thomson limit? Well, just to define our momenta, let me draw a diagram again. So here I have an incoming electron with momentum P1, outgoing electron with momentum P2, and the photon has a momentum K. And so the Thomson limit corresponds to the case where both the in and outgoing electron are on shell, so their p squares are equal to m squared. And the momentum of the photon, which by momentum conservation is the difference of these two, is 0 or goes to 0. So this corresponds to a particular experimental situation that one can realize where it would basically correspond to interaction of an electron with a classical electromagnetic field, a static classical electromagnetic field, because the photons in that field have negligible momentum. So now, how can we derive a counter term from this for our coupling? So first of all, let me write this blob here, which again would include all potential loop corrections and stuff like that as a capital gamma mu. So this is different from the little gammas. Needs to have an index mu because the photon has an index mu. So as a formula, this diagram that I was just drawing over there, and then be expressed like this, where I have the two spinors, u and u bar, for the in and outgoing electrons. Sorry, the other way around. This is P1. And this is P2. And in between is this symbol gamma. And now the renormalization condition that this should correspond to the strength of the coupling in the Thomson limit tells us that this should become just I times E times little gamma mu in that limit. And as a matter of fact, because k goes to 0, it means that in this limit, P1 and P2 become equal. So not here, but equal to. Okay, we have another question. What if the fermion line is an inner line? Is the Thomson limit still applicable? Not exactly. So the Thomson limit really corresponds to an actual situation that we can represent by an experiment. So therefore, these are supposed to be external electrons, and they are supposed to be on shell. So this really corresponds to an electron that we can observe moving through an electromagnetic field. And the second question, k squared much less than m squared approximation. Well, that's implied if k is 0. Definitely. Yeah, it's exactly 0 in the Thomson limit. Okay, so now let me take this gamma and split it into two parts. One is the tree-level contribution, which is the Lagrangian coupling E0 times little gamma mu. And then something that I call delta capital gamma, which includes all the possible vertex corrections So things coming from diagrams like this, for instance, and so forth, right? Any loop order again. So in principle, this would be already enough to write down an expression for computing the counter term for the coupling. But it's actually customary to take advantage at this point of a Ward identity. And this Ward identity says that if I take the vertex corrections, delta gamma, and now the photon momentum is not zero, some non-zero photon momentum k. So I take this vertex correction and I contracted it with k, then this is equal to a difference of 2 electron self-energies. One at p plus k, so the momentum of the outgoing electron, the other one at momentum p, the one of the ingoing. Now in our case, we are interested, of course, at the limit k going to 0. And if I take this formula and I rearrange it a little bit, this gamma on the left-hand side then has the same in and outgoing momentum if k goes to 0. And on the right-hand side, I now include this k mu, so I move that to the right-hand side. And I have the difference of self-energies. And I need to take this expression at the limit k going to 0. And this limit is basically nothing but derivative with respect to the momentum. So we take the derivative of the self-energy with respect to momentum. And so this is kind of cute. It allows us to express all the vertex corrections that we have in terms of self-energies. So we would actually only need to compute self-energies for doing this. Now, we may think we are done after we have renormalized mass and coupling, but in fact, there's some more work we need to do. We also need to renormalize the fields. And the reason for that is that if we consider some physical process, maybe a scattering process, there can be all kinds of interactions happening in this blob. I can also have loop corrections only on the external legs, something like this maybe. Right, so this is a self-energy correction on one of the external legs. And so that obviously will modify the propagator of this particle, but I want to relate this particle to a basic propagator that I use actually for connecting to my experiment. And so this additional loop correction here that happens on the external leg is called a wave function correction. I want to absorb that by redefining the field. So I get rid of that. So this can happen for an electron, as I was drawing here. It can also happen for the photon. So I need to do this for both fields. So I write the electron field in the Lagrangian as some renormalization factor times the physical field, and same for the photon field. And as before, these, for both fields, these factors can be written as 1 plus a counter term, the idea that this counter term is much smaller than 1. Another question, which is claimed to be dumb, but probably isn't. Does this renormalization scheme have a name, like on-shell MS bar? That is a very good question, and I will come back to that a little later, but in principle, what I'm talking about here is the on-shell scheme. Another question, if gamma mu, I guess this is capital gamma, is defined for external electrons, then how can we be sure that the gamma mu used for the vertex when the electron is a virtual particle is the same gamma mu? So the reason that is the same gamma mu comes from Lorentz invariance. So this capital gamma depends on the external momenta, P1, P2 here. K basically can be gotten from momentum conservation. For the renormalization condition in the Thomson limit, we use specific values for P1 and P2. They need to be on shell. But if they are off shell, then basically Lorentz covariance tells us that if we write gamma mu in terms of building blocks for which we know the transformation under Lorentz transformations, then we know how it behaves for any other momentum. So this is similar to what we just did for the electron self-energy, right? We wrote that as two pieces, the scalar piece and the vector piece, and we know each of can depend only on p squared. The gamma is in front of the vector piece. So at that point, if we have this, and we have an expression that contains the dependence on p squared, I know how this looks both for on and for off shell momenta. And so the same works for the vertex correction for the gamma. You can basically also, you could write this out in terms of things that go with different gamma matrices. There are terms with 1 and 2 gamma matrices, which we can get. I'm not writing them down here because of lack of time. And terms with 3 gamma matrices can then be reduced to simpler ones. Is there an assumption in dividing by K mu in this way, especially for photons, K mu must have more than one non-zero component? Yes, before we take the limit, definitely, right? So in the formula where we take a limit from, we want a non-zero K. But in the end, we want to take the limit where all 4 components go to 0. And that limit gives us the derivative. Good, so now we need some renormalization conditions for these field renormalizations as well. Let's start with the electron. So once I include the field renormalization, actually what I wrote down before is not entirely correct. What we get in the denominator of the propagator now needs to include an extra factor z psi. And then we have the self-energy just as before. So this is how now the denominator of the propagator looks like. Even though each field gets multiplied with a square root of z psi, in the propagator, because there's one in and one outgoing field, we get the square root squared, so we get z psi without a square root. And what we want is that the z psi basically compensates the wave function correction, which is inside of the self-energy, in the limit where this is a real external particle, so p slash goes to m. So in that limit, we basically want this to take the form of the basic tree-level propagator, but with a renormalized mass. Now, writing the condition like this is not perfectly convenient because on the left-hand side, I have the unrenormalized mass m0. On the right-hand side, I have the renormalized one. But I can fix that by taking derivatives on both sides of this equation. And I take the derivative with respect to momentum, contract with another momentum. Then on the left-hand side, I get a p mu, and the derivative acts on the p slash. There's the renormalization constant in front. And so what's left after taking the derivative of p slash is a gamma mu. This is from what I get from the first term. And then I have the second term where I need to take the derivative of the self-energy. On the right-hand side, again, derivative acts on the p slash. That gives me a gamma mu. And then this gets multiplied by a p mu. So now I can take this expression and solve it for my counter term, delta c psi. This becomes p mu divided by m. And the derivative of sigma. And after taking the derivative, I set p slash equal to m. If I plug in the decomposition I had earlier of sigma in terms of sigma s and sigma v over here, I can write this out in terms of these components. So this becomes the vector part at p squared equals m squared plus 2 times m times the derivative of the vector part. I call that sigma prime, plus 2 times the derivative of the scalar part. And this is an expression you will find in various sources. Now let's do the same for the photon self-energy. There was a question, is there a minus sign? Where specifically? Shall we unmute delta z psi minus p? Okay. I see what you mean.
Yeah, I understand is that p mu gamma mu is cancelled with the right hand side, and then this p mu delta psi gamma mu plus that stuff equals to 0. So is there a minus sign?
Yes, there are minus sign.
Are we going to use the expression?
We don't. I'm pretty sure that the formula in the end does not have a minus sign, although I might need to check. Let me check that until next time, and I will get back to you when we have the next lecture. So the photon, because it has an external Lorentz index, then the photon self-energy has two of these indices, one for the in and one for the outgoing photon. And if we decompose that into different Lorentz vectors, there could be a metric tensor G mu nu, or there could be something that has two times the photon momentum, k nu. And it turns out that instead of just splitting into the G mu nu and the k nu part, it's better to split into one factor that goes like this, with the difference of the two, and another factor that has only a k nu. The reason is that we do this way is that those two factors are then projectors. So if you multiply one with the other, you get 0. And the two parts are called the transverse and longitudinal component. There's another word identity that tells us that if I take the photon self-energy and I contract it with the photon momentum, it's supposed to get 0. This immediately tells us that the longitudinal part is actually 0. Okay, sorry, there was another question about before. Should it be 2m squared times sigma v? No, it would be just 2 times m, because as you can, if you just look at the dimensions, the sigma v has 1 power of p in front of it. So just one mass dimension in front of it, not 2. So then, because the longitudinal part is 0 of the self-energy, we are just left with the transverse part of the self-energy. And for that, one can do a Dyson summation, just as we did for fermions. I'm not going through the steps. The result is we have the transverse part, which has the self-energy in the denominator now. And we have a longitudinal part where we just have the tree-level piece, but no self-energy because that is 0. Now, the renormalization condition that we apply for the photon field renormalization is similar to what we did for the electron. We say that this counter term, ZA, so we need to introduce a counter term here for the field. It comes in here. This counter term is supposed to compensate the wave function correction that comes from the self-energy when the photon is on shell, when it becomes a real photon with k squared equals 0. So in that case, the two are supposed to compensate, and what we have left is just again the tree-level piece, which would be just a k squared in the denominator. And then by doing the same thing as we did for the electron, so we take derivatives on both sides of the equation, then up to a minus sign that I guess I need to check, we get that this counter term is given by the derivative of the transverse part of the self-energy. Okay, we have a question. What is this? Is this the full propagator? Yeah, so this line where I wrote Dyson Summation, this is the propagator involving the all the self-energies. Yes, all the self-energy corrections. Another question. Generally, you need to fix a gauge for the photon propagator. Very good point. That is absolutely true. What is the gauge in this case? So the gauge in this case is Feynman gauge. I should have mentioned that. Thanks for pointing that out. Good. So as you noticed, as is indicated here with red, what we needed to do once we introduce these field renormalizations, we need to plug them in all the different places where we actually have fields, right? So in the propagators, we needed to plug them in. So as a matter of fact, if we go back to our coupling renormalization, we need to put them in there as well. So what I wrote before is that the renormalized coupling, E mu, in the Thomson limit, was given by the three-level piece plus the vertex corrections. Now I need to include also field renormalizations. So there's an in and an outgoing electron field. So I get 2 square roots, makes a Z psi. And there is also a photon field, but only one. So that still has a square root. This correction over here we saw earlier with the help of the water identity, we could write as this derivative of the self-energy. And these various field factors over here, recognizing the fact that we can write each of them as 1 plus a delta, I can basically spell that out as 1 plus delta Z psi plus 1/2 delta ZA. And if I extend this under brace to actually include the E0, and I write also that in terms of a counter term, there's also delta ZE, counter term for the coupling. If I take all that together, I have 1 plus delta ZE plus 1/2 delta ZA plus delta Z psi plus this derivative, self-energy. But now, if I look a little up on the same slide over here, I have a condition for the field renormalization of the electron already, and I can plug that in down here, and lo and behold, I see that those two terms exactly cancel. They become 0. Then what I'm left with are these two terms, the one for the photon field renormalization and the one for the coupling renormalization. And I basically see now that I can get the coupling renormalization from the one for the photon. So I actually don't need to compute anything extra to get that. Okay, so we have a couple more questions. Does the decomposition of transverse and longitudinal mode depend on the gauge choice? Well, so the fact that you can decompose it into those two modes does not depend on that. All we use for that is Lorentz transformations, properties under Lorentz transformations. But of course, the specific value of, well, it's the longitudinal part. The longitudinal part that I have over here, which is just minus I divided by k squared, in the Feynman gauge, in a different gauge, it would look differently. Another question, after the Dyson summation, how come we still have the second term? So the second term comes from the tree-level piece. So sigma includes the self-energies, but it doesn't include the tree level. So sigma includes all the loops. The Ward identity tells us that the loop piece for the self-energy is, for the longitudinal part, sorry, the loop piece is 0, but there's still a tree-level piece. So we didn't sum anything here. This just comes from the very basic tree-level diagram like this. This still has a longitudinal contribution. Actually, in Feynman gauge, it just has a G mu nu part. And if we split it up into transverse and longitudinal, we need to have those two parts. Then another question. Oh, that's an answer to that, actually. Oh, sorry. There's a gamma mu term multiplying the first 4 terms. Down here, you mean? Yes. So the underbrace is basically only about these 3 coefficients. Oh, this is here over there. Sorry. Okay, now I know what you mean. Yes. So there, he messed it up. So we should close over here. And then there's a gamma mu in there. Right. That's correct. What is delta ZE? So this was the very beginning. This is the counter term for the charge or for the coupling. Over here. And can you please repeat why we get 0? I guess this is for the green 0. Yes. Okay, good. So we get this, we use the Ward identity to get this derivative for sigma here. This is the one that is on the right-hand side of this equation. And then we used what we derived up here in what is circled by green for how we can compute the field renormalization for the electron. We plug that in here. And when we do that, we see that those 2 terms cancel exactly. Sorry, I also did I mess up a gamma somewhere? Again. Something gets mixed up with writing all these formulas. Sorry about that, but yeah, I lost the gamma somewhere along the way. I can't fix it right now. Don't want to spend too much time searching for the typo, but somewhere. Yeah, I will check the minus sign in this gamma until tomorrow. Okay, now actually looking at this result that we derived for the charge renormalization, let me just present you from what we get if we do an explicit one-loop calculation. And I'm just not going through actually how one does this calculation. I'm just giving you the result. I'm computing one-loop diagrams to the photon self-energy because that's what I need for the photon field renormalization. So there are fermions inside the loop. And I do this in dimensional regularization. The result I get is the fine structure constant alpha divided by 3 pi. Then I have a divergent piece, 2 divided by 4 minus d, where d is the number of space-time dimensions. Some constant that I always get if I do dimensional regularization, Euler gamma. And a logarithm of m squared divided by 4 pi u squared. Mu is this mass dimension parameter that we need in dimensional regularization. And m is the mass of the fermions running in a loop. So this is the result we get in QED, but if we kind of mentally jump ahead and think of the standard model, all fermions in the standard model could appear in the loop. And so for this derivative of the self-energy, we would get a sum over all these fermions. Alpha divided by 3 pi is not changed. Then these different fermions have different electric charges. So I need to account for that. So this QF accounts for the charges. It would be 1 for an electron and would be something fractional for quarks. If I have quarks, also I need to recognize that they come in 3 different colors. I need to sum over those colors. So this is a color factor that would be 3 for quarks and 1 for leptons. And then I get all these factors that I have above and this logarithm of the fermion mass, which now, of course, is different for different fermions because they have different masses. That's a pretty simple formula, but there is a problem with this formula because I need to put in masses for all the fermions. For electron, muon, tau, that's no problem. They have been measured very precisely. You can find that in the PDG or something like that. But for quarks, in particular for light quarks, it's not clear what this mass is supposed to be. Because, as you may know, quarks can never be observed in isolation. So nobody has ever seen an up or down quark or something like that. We only see bound states of them. And if we never see a quark in isolation, we really don't know what are their masses. This is not something we can just go out and measure. They're not very well defined. For a bottom quark, the situation is not as bad because even though we also don't see a bottom quark in isolation, its mass is relatively heavy. So if you look at a B meson, most of the mass of the B meson comes actually from the bottom quark itself rather than from the binding energy. But for up, down, and strange, the situation is much worse because their masses are of the order of the binding energy or less. We can argue how much less, but they are definitely subdominant and so really don't have any idea what this mass is supposed to be. So how can we deal with that problem? Well, the solution is, instead of using masses here, we use some other inputs. And we get these other inputs by using a so-called dispersion relation. And I kind of would like to point it out because actually dispersion relations, they appear in different parts of particle physics. This is, where they appear in the standard model, but these are really interesting properties that one can use every now and then. So the idea is we need to compute this derivative of the self-energy. Let me define a new function, which I call capital pi, which is self-energy divided by q squared. So you see if q squared goes to 0, that produces a derivative. And now pi of 0, I want to write as pi of 0 minus pi at some high energy scale, like maybe the Z mass. Because it can have an imaginary part, I only take the real part here. And well, I subtracted that, so I have to add it back. So this last term, this is something I can actually compute much more reliably, because it turns out that this one depends on the quark masses. Only through terms of fermion mass squared divided by mz mass squared. So there are no logarithms like the one up there in this expression. And because the Z mass is so large, I can basically set that to 0 for anything besides the top quark. So I can compute this part reliably. The other part over here, I cannot compute reliably because that still contains this nasty logarithm. So I call that delta alpha. And now I can use this dispersion relation, which uses an analytic property of the self-energy. And I won't have time to go through the derivation here in the lecture, but I have it in my lecture notes. So I do encourage you to look at that. Basically, the key part that is being used here is that the self-energy is an analytic function everywhere in the complex plane, the complex taking its momentum as a complex function, complex parameter, sorry, complex variable. It's an analytic function everywhere except along the positive real axis where it has a branch cut. I kind of see that it has a branch cut because we have a logarithm, right? The logarithm has a branch cut, so the self-energy has a branch cut. And so we integrate around this branch cut. And what we get from that in the end of the day is the following expression. In 3 factors, then I have an integral. Has the integration variable s prime, and inside this integral is this quantity r, and this is defined as the ratio of the cross section of E plus E minus to hadrons divided by the cross section of E plus E minus to muons. To get to this from what we had before. What one was using the optical theorems. So we have the self-energy, photon here, quarks inside the loop. Now we use the optical theorem to split that up. Becomes now a matrix element of photon going into a pair of quarks. Quarks, of course, hadronize. So that's why we have something going to hadrons. And then we just attach E plus E minus on both sides. We know how that coupling looks like, and we get this cross-section. And this is something we can take from data. So these cross-sections can be measured. And if we measure them over many center of mass energies, we have enough data to put into this integral, and then we can perform this integral numerically. And there are many people who do this, have been doing this for many years. Few references I mentioned with archive numbers in my lecture notes. Let me just write down one of them here. So this is one archive number of somebody who does this exercise, taking this data and computing this shift delta alpha for that. Okay, we have a few more questions. Is the statement about the light quark masses due to the intrinsic complications of QCD or just ignorance and imprecision in current measurements of quark masses? It's the former. It is really about the intrinsic complications of QCD. Because there are no isolated quarks, there's no reasonable meaning of a perturbative, of a quark mass in a perturbative calculation. That basically just doesn't exist. If you do a lattice calculation, you can in principle compute things in QCD, and there are quark masses that you need to put into your lattice calculation as a free parameter that need to go on. But a lattice calculation is a conceptually different beast than what we are doing here, where we compute things order by order. So whatever masses they use in a lattice calculation have nothing to do with the masses that we would need to put into our self-energy correction. So it doesn't help us. Another question, at what scale do we use the quark masses at? Well, the answer is we don't use the quark masses. That's exactly the trick. What this is probably referring to is if one were to renormalize the quark masses in the MS bar scheme rather than in the on-shell scheme, they would depend on the scale. And that's another ambiguity that comes into the game, which would make things even more problematic. But the solution that we use is we don't use the quark masses. We express the self-energy in terms of this R ratio, which we can get from data. Another question, why did we choose the Z boson mass scale and not another scale? Why not the QCD scale, which is relevant for light quarks? Great question. So in principle, the Z mass as a scale is completely arbitrary. The only condition is it needs to be a scale that is much larger than the QCD scale. So the W mass would be fine. You can just pick 50 GeV, you can pick 200 GeV, it doesn't really matter at all. The Z mass is kind of, what has become the default to be used there, but it needs to be a large scale for the reason that in this term that we compute over here, which depends on the masses in this ratio, so the quark mass divided by whatever scale we choose over there, that needs to be small so that we can compute this reliably. If instead of MZ we were picking lambda QCD here, this would not be a small number. And one more question, why the pi of Z has different dependence on quark masses compared to the pi of photon logarithmic? Why? Well, I mean, the whole expression, of course, is a little longer. So as a matter of fact, the whole expression for this pi, I didn't write it down here, but it involves several logarithms and so on. It's a little lengthy. It's just one line, but it's a little lengthy. And if you were to take that expression and expand it in powers of mf squared over mz squared, then you get basically a power series without a logarithm. Now you can kind of see that. So generally, if I have pi of q squared, and I were to do an expansion in powers of mf over q squared, so I would get a leading piece which does not depend. I would get the next two leading piece which depends linearly on the mass squared and so on. And now you see, if I were to take the limit of this expression for q squared going to 0, I cannot do that, right? Because I was writing down an expansion here, assuming that this is a small parameter. When q squared goes to 0, it's not a small parameter anymore. It actually becomes large, and the whole expression changes character. And I get something that's obviously singular in that case, and it turns out it becomes a logarithm. Ooh, somebody's interested in finite temperature. In the finite temperature piece, it seems there is a preference 3+1 decomposition, and the projector of longitudinal and transverse mode and Coulomb gauge is rather different. I'm referring to the form of gauge mode. Yes, that is definitely correct. So all I'm doing here is for zero temperature case. In finite temperature field theory, the decomposition of the self-energies would be different. Do we find pi mz squared analytically or experimentally? So this piece here circled in red, we compute that theoretically. The experimental part is only this difference over here, what I call delta alpha, which can be interpreted as a shift in the fine structure constant due to this renormalization. So that we get from experimental. Okay, very good. Yeah, so we had many questions. I guess we are kind of out of time, so I should probably stop over here. I don't know if the organizers want to say some final words.
Great, thank you. Any more pressing questions? We already had a number of them. If there's any longer discussions, you're welcome to continue them over in the Slack.
Sure.
Have we announced the names for the discussion sessions on Wednesday and Friday, Ethan? Or is that still up in the air?
I think we're still waiting to confirm that. So we'll announce details for those tomorrow or Wednesday.
All right.
And yeah, we'll work on fixing the discussion room. So watch the Slack general for that. But otherwise, I think there's nothing else to announce. So we'll wrap up the official activities for the day. We'll see everyone at 9 a.m. tomorrow.